Okay, good afternoon, everyone. My name is Meori, and I'm from the Department of Robotic and Mechanical Engineering, and this is in South Korea. Today's topic is advanced handheld microsurgical system using a Hall sensor and magnet trocar for retinal microsurgery. The epiretinal ophthalmic disease, such as epiretinal membrane (ERM), affect around 7 to 12% of people aged 50 and older. The ERM develops as a fibrous layer on the retinal surface during healing after injuries like posterior vitreous detachment. This membrane obscures the optic nerves, resulting in blurred vision, double vision, distortion, and difficulty in seeing fine detail. Typically, this membrane is very thin, measuring around 60 micrometers. The membrane must be physically removed through epiretinal membrane peeling (ERMP). This surgery presents several challenges. First, when peeling up the thin membrane, a surgeon may accidentally touch the retinal blood vessel, which can lead to the bleeding. Second, the surgeon must manage their hand trimmer that costs 100 to 200 micrometer displacement with 8 to 1200 frequencies. This tremor significantly increased the risk of the retinal damage during surgery. As the advantage of compactness, we focused on the handheld device. So distance measurement, sample surface, and tremor compensation technique have been explored. Compensation using optical coherence tomography (OCT). OCT provides high precision distance measurements, and it can respond to the unexpected movement by identifying the distance between the reflective surface and the sensor. However, it is limited to measure along single axis in three direction and short working range. Some researchers have attempted to improve performance with Kalman filter and convolutional neural network, but the inherent limitation of OCT technology remain. Various non-distance measurements to the sample surface and tremor compensation technique have been explored to reduce hand tremor. Inertial measurement unit (IMU) that use accelerometer and magnetometer suffer from drift and resolution problem, lowering their accuracy. Vision-based system using LEDs and cameras have sideline obstruction because the sensing workspace is limited. Electromagnetic tracker provides 6-axis tracking. However, their slow update rate makes them unsuitable for real-time tremor compensation. Reference control loop speed is 500 Hz. Since the positional relationship between surgical tool and the target is unclear, it is relatively difficult to respond to patient or eye's unexpected movement. Our proposed studies introduced a handheld microsurgical tool with a 3-axis Hall sensor. Hall sensor is attached to the pitch-tip motor shaft and detects the magnetic flux density. This magnetic flux is generated by a ring-shaped permanent magnet which functions as a trocar of the square surface of the eye. The trocar acts as an entry point for needle into the eye while also protecting the surrounding scar tissue. This system has defined the positional relationship between the eye and the tool, enabling real-time tremor compensation. This method overcomes the limitation of non-distance measurement to sample surface system and provides safe maneuver in retinal surgery. Let's focus on the relationship between the magnet trocar and Hall sensor. Using multiple coordinate system and vector, we have defined the relationship between the trocar and the sensor. RMO and RMI represent the outer and inner radii of the magnet respectively, while LM is height of the magnet. This slide explains how to find the permanent magnet position. We use Biot-Savart law for magnetic field model to estimate magnetic field as a magnetic dipole. In this law, magnetization constant is calculated from the volume of the cylindrical permanent magnet. So this constant is changed to ring-shaped permanent magnet. Additionally, distance factor R between the Hall sensor and the magnet is defined. Three orthogonal components of the magnetic flux density are used as follows. These components can be simplified because the magnet and sensor are aligned along the z-axis. The position of the ring magnet is calculated from magnetic flux density component. Also, constant distance is used from the fixed coordinate between S and projection and S. Finally, the effective distance between the two and the surface of the magnet is used as a control variable. Let's see the magnetic flux density simulation. We performed simulation using ANSYS ADT. The simulation was set up with neodymium as magnet material and IROS boundary condition below. This allows us to analyze how magnetic flux density varies with distance, providing insight into the sensor response. The results show that the system can reliably detect changes in magnetic flux density within the operational range. Let's move on to calibration part. Relationship between the magnetic flux density and distance is measured in real environment, and this plot can explain the tendency of distance and magnetic flux density. Let's see the hysteresis measurement. We utilize a motorized stage with the sensor forward and backward in 0.1 millimeter increment over 6 steps along X, Y, and Z axis. At each step, the sensor reading were compared with the magnetic flux density value of forward and backward. A ring-shaped permanent magnet is rotational symmetry. That means Bx and By are equal. And we calculate a p-value at each step. It indicates that the sensor performs consistently and accurately, providing a reliable measurement within the specified range. These are whole results of hysteresis measurements. Magnetic flux density of vectors B, Bx, and Bz are calculated, measured, and compared to each step. And we obtain p-value less than 0.001 in every step. Let's move on to experiment part. The condition of our tremor compensation experiment using an artificial eye model and porcine eye. The magnet and sensor were positioned at 1,000, 2,000, and 4,000 micrometer target distance. The tremor amplitude was measured before and after the activation of the compensation system. RMS errors were compared to the typical error 100 to 200 in artificial and porcine eyes. These experiments show that the proposed system effectively compensates for tremors. This video demonstrates a tremor compensation system using artificial eye model and ex vivo pig eye. In this video, the red arrows represent the target distance as 1,000 micrometer in both samples. Let's see the experimental results, including artificial eye model and ex vivo pig eye. So finally, RMS error of compensating hand tremor is measured in this table. In the conclusion, we have developed a handheld microsurgical system that provides real-time tremor compensation using a 3-axis Hall sensor and ring-type permanent magnet. The system was validated through experiment with artificial and porcelain eyes and calibration tests, showing significant reductions in tremor amplitude. In our future work, we are implementing it as a multi-degree freedom system with the whole sensor array to additional in vivo testing to evaluate the system performance in preclinical conditions. Thank you for listening. This work supported by Technology Innovation Program, funded by Ministry of Trade and Industry Energy and Digits, R&D Program and Ministry of Science, ICT and Technology of Korea. Thank you for your attention.
Great, thank you very much. So, because